Welcome you all to the session of Solutions for GATE 2022 Mechanical Engineering with Heat Transfer subject. Moving on to the first question. Consider a one-dimensional steady-state heat conduction process through a solid slab of thickness 0.1 meter. The higher temperature side A has a surface temperature of 80 degrees centigrade and the heat transfer rate per unit area to low temperature side B is 4.5 kilowatt per meter square. The thermal conductivity of the slab is 15 watt per meter Kelvin. The rate of entropy generation per unit area during the heat transfer process is dash watt per meter square Kelvin. Here he has given Q heat transfer rate 4.5 kilowatt per meter square. Thermal conductivity is 15 meter per Kelvin. For suppose this is the wall taken, let this thickness be 0.1 meter. Here 80 degrees centigrade at surface A and here at surface B. When I write in terms of Kelvin, it will be 353 Kelvin because 273 plus 80 and this is the slab, right? Now we will be trying to find the temperature at point or surface B. We all know that Q is equal to K into dt by dx, that is K into TA minus TB by T. That gives 4500, the value of Q, changing kilowatt to watt per meter square, 15 the value of K, 80 TA minus TB by thickness is 0.1. From here, if you modify, 80 minus TB will be is equal to 300 into 0.1, that will be 30. Now TB is equal to 80 minus 30, which is 50 degrees centigrade. That will be 50 plus 273, which gives you 323 Kelvin. Now the heat generated is exit minus entry. Steady state, if we consider, heat generated is SE, that can be written as Q by TE, mass flow rate by temperature, minus entry temperature or inlet temperature. Q by TB minus Q by TA. Heat flow is same, that will be 1 by TB minus 1 by TA. We will be getting it as 4500 1 by 323 minus 1 by 353. This will give you around 1.184 meter square Kelvin. That is heat transfer process. Heat transfer is 1.184. This will be your answer for the given question. This will be the answer for the given question. Moving to the next question. During open heart surgery, a patient blood is collected down to 25 degrees centigrade from 37 degrees centigrade using a concentric tube counterflow heat exchanger. Water enters the heat exchanger at 4 degrees centigrade and leaves at 18 degrees centigrade. Blood flow through the rate during the surgery is 5 liter per minute. Using the following fluid properties: fluid with density, blood density is 1050 kg per meter cube, specific heat is 3740, water 1000 kg per meter cube with 4200 joule per kg Kelvin specific heat. Effectiveness of the heat exchanger rounded off to 2 decimals. For example, this is a counterflow heat exchanger. Heat loss by blood is equal to heat gain by water. This is the basic condition. Now, MCP delta T will be your formula generally. That is, for suppose, if you take a counterflow, this is at 37 degrees centigrade, drop down to 25 degrees centigrade. Blood is this, mass flow rate of blood, and 5 liter per minute you need to convert into kg per second. This will be water, where from 4 degrees centigrade it has gone to 18 degrees centigrade. M dot 5 liter per minute, if I convert them, I need to convert them into kg per second. This will be 0.0875 into Cp, specific heat, delta T 37 minus 25. Mass flow rate of water is not known. Cp is 4200, delta T is 18 minus 4. From here, mass flow rate of water you need to find. You will get around 0.0667 kg per second. And the question is asking you effectiveness, right? What is the formula for effectiveness? Water minus inlet of water, this is exit, by blood to water. That is, we need to find MCP of blood, 327.25 kilojoule per kg second you will get, Kelvin second you will get. M into Cp, both are known to you. MCP of water 280 kilojoule per Kelvin second. Now substitute in this formula 18 minus 4 by 37 minus 4, which you will get as 0.4242. The effectiveness 0.4242. This is the formula. This is the answer for the given question. Moving to the next question. Theoretical question, 1 mark question. In the following two-dimensional momentum equation of natural convection over a surface immersed in a quiescent fluid at temperature T infinity, G is the gravitational acceleration, beta is volumetric thermal expansion coefficient, U is kinematic viscosity. U and V are velocities in direction of x and y. U into dou U by dou x plus V into dou U by dou y equal to G into beta T minus T infinity plus V into dou square U by dou y square. Term G into beta into T minus T infinity represents ratio of buoyancy force to viscous force per unit mass, ratio of internal inertial force to viscous force, buoyancy force per unit mass. Basically, G beta delta T. Where will we use this? This is isobaric volume expansion, we say. Isobaric volume expansion. We write this beta as 1 by V dou V by dou T by K, right? Where G beta delta T signifies buoyancy force which arised due to change in density. That will be buoyancy force per unit mass, option D. Buoyancy force per unit mass will be the appropriate right answer for the given question. Moving to the next question. Question number 4. Consider a solid slab with thermal conductivity K 10 watt per meter Kelvin with the thickness of 0.2 meter of infinity extent in two different directions shown in the figure. Surface 2 is exposed at 300 Kelvin of the fluid flow with the T infinity of 293 Kelvin and convective heat transfer coefficient H equal to 100 watt meter per minus 2 or watt per meter square joule. Surface 2 is opaque, diffuse and grey with emissivity of 0.5. Heat exchanger heat by radiation with very large surrounding at 0 Kelvin. Radiate heat transfer inside the solid slab is neglected. Stephen-Boltzmann's constant is 5.67 into 10 power minus 8. The temperature T1 of surface 1 of the slab under study condition. So he has given the temperature, fluid temperature, H value, T2 temperature and K thermal conductivity. From here, I can clearly write heat transfer from conduction will be is equal to heat transfer for convection and radiation. This is K into delta T by delta Y distance, H into surface 2 minus T infinity plus sigma into epsilon into surface 2 power 4 minus ambient power 4. This is the formula. Substituting 10 into K, T1 I don't know, minus delta 3, T2 300 by distance is 0.2 meter thick. You can clearly observe a thickness of 0.2 will be equal to 100 into 300 minus 293 which is already given plus 0.5 into 5.67 into 10 power minus 8 into 300 power 4 minus 0 power 4. Radiation, I have substituted all the values of radiation here. Here surface temperature is 0 Kelvin, T infinity is 293, T2 is 300. From here, if I found the value of T1 on calculation, I need to get a value of 318.5927 Kelvin. This will be the appropriate answer, that is surface 1 of the slab under study condition 318.5 Kelvin. Both conduction, convection, radiation formulas are used here. K into delta T by delta X or delta Y, H into Ts minus T infinity, sigma epsilon Ts surface minus your temperature which is given as 0 degrees also, right? That is with large surrounding temperature. This will be your answer for the given question. Moving to the next question. A flat plate made of cast iron is exposed to solar flux of 600 watt per meter square at an ambient temperature of 25 degrees centigrade. Assuming that the entire solar flux is absorbed by the plate, cast iron has a lower temperature observability 0.21 with the Stephens-Boltzmann constant 5.669 into 10 power minus 8, which is a standard. Under the aforementioned conditions, the radiation equilibrium temperature of the plate in dash degrees centigrade round off to nearest integer. For suppose this is some cast iron plate. This is cast iron. Solar flux is 600 and the temperature is 25 degrees centigrade, which is ambient or infinity. So the sky radiation is totally getting concentrated on the cast iron, approximately same spectral region as that of surface emissions. So we can say absorptivity of sky is equal to emissivity, which is 0.2. When you balance the energy cast iron radiation, that is 600 is equal to absorptivity psi sigma T1 power 4 minus T2 power 4. How much is given? 273, because 0, right? No, he has given around 25. 25 plus 273 will get 273 plus 25 whole power 4. This is 600, 0.21, 5.669 into 10 power minus 8 into T1 power 4 minus 298 power 4. From here, find the value of T1. You will get around 491.34 Kelvin. That is 218.34 degrees centigrade. 218.34 degrees centigrade. This will be the right answer for the given question. These are the questions of GATE 2022 for heat transfer subjects. Hope you people have understood. Thank you, students.